Okay, so this will be the second part of my lecture, and now somehow I will change the topic, and I will move into this, it's device and QKD, but the motivations. To explain the motivations, the main motivation is the existence of quantum hacking attacks. This is why people thought about other possibilities to make quantum distribution that are robust against the hacking attacks I presented. So remember what I said. Basically, the main problem comes from the fact that it's sometimes very difficult to meet what the theory demands, so the theory requirements. These are difficult to meet in the implementation. So there is some sort of, here there is a gap, okay? And here you prove security here, but you want security to hold here. And again, this problem was also related to what I say, certification. Okay, so here you say things like that a particle is described by a vector in a hyperspatial dimension 2 that might be difficult to certify. So somehow, device-independent QKD, the main objective is to simplify this. Okay, to make to close the gap between implementation and theory, so that you make sure that the implementation is secure, because basically there is no secure with the theory. In the theoretical part, you have a mathematical proof that tells you that something is secure. And for that, now, the second part of my lecture is going to be about boxes. So all my lecture is going to be about boxes, because you remember also what I said before about the provider. This is what you get from the provider. So if you want to buy a cryptographic solution, you go and you get, let's say, okay, you get a chip, but let's think for a while that it gives you a box, okay, and it says this is your quantum, the devices you have to use for quantum distribution. So all my talk now is going to be about boxes. So there is Alice, Bob. They go to the provider, and the provider, they ask from the provider, and they should get two devices that I will just show as a box. And in this box, Alice, you can see it in a pictorial way. She has two buttons, and Bob has two buttons. Okay, so Alice and Bob go to the provider, they say, give me a device, and what I only demand from you is that this device has two buttons. Okay, or if you want, it has a knob that you can put into different positions or whatever. It can be something, a microscopic action that you can implement on your device. But now I represent with buttons, but it can be, whatever you want, but it has to be something that you can implement on your device. And then the device has two possible results. Here I represent with two lights. And somehow when you press one of the buttons, one of the lights is on. Okay? Again, I represent this with a light because I think it gives it's easy to understand, but it can be whatever. So somehow the idea is that you have a box. In this box you can perform an action, and as a result of this action you get a result. Okay, so if you want another way, you have an action which is represented by some classical information. You can feed your device with classical information, and then the device gives you an output, and Bob can do the same. Okay. So now you go to the provider and you ask you ask these two boxes. Alice has one, Bob has one, and they don't want to put any trust on the provider in the sense that they don't want to believe. So in the standard you get before, you get these boxes, okay, from the provider, and now you say you ask the provider, please tell me, how do I know that this is quantum? And the provider will tell you, you have to believe that I hear when you press a button, there is a quantum particle that lives in a hyperspatial dimension 2, and this information is called a polarization, and this information is sent to the other particle, and here when you press a button you get an output, and this corresponds to a measurement on the sigma x or sigma z or whatever. Okay, so there is a lot of specification of the devices that you need to trust from the provider. And as I was telling you, the problem is that the specifications that the provider needs to guarantee you for security sometimes are difficult to fulfill. So now what you want to do, you don't want to put any trust on this. Okay, so you get a box from the provider, and you don't want to make any assumption about what is happening inside the box that produces the output given the input. Okay, so here there might be whatever. It might be a qubit, but there might be even a demon, okay? Or there might be, I don't know, whatever. Okay, there is a process. Of course, you believe in quantum physics, so there might be a quantum process that takes this classical information and gives you some classical information, and the same above. So this is why this is called device independent, because it's independent of the inner working of the devices. So okay, so Alice and Bob get these two boxes, and they go to their labs, and they want to test that they satisfy something that is useful for security. And the only thing they can test here, the only thing they can do with the box, they can press buttons and see which light is on. Okay, so Alice and Bob have their boxes, and they start in a synchronized way. They start pressing buttons and collect and see which lights are on. So they repeat this a given amount of times. So in this way, they try to characterize their devices, but they do it from the outside. So they don't try to make any tomography or any characterization of the device beyond what they see. So they see that when I press a given button, one of the lights is on. So when you repeat this process many times, you can think of the honest parties. They can count how many times I observe a given output when I press a given input, and Bob can do the same. So you repeat this many times, and at the very end, they can reconstruct the probability that the first device gives output A, and the second device, oh sorry, here. So you can repeat this many times, and here you can see the probability that you observe output A and output B when you press button X and button Y. Okay, you should understand that this is something you don't have to trust the provider. You just press button and you see the output, and you count how many times this happened. And this is something that you don't need any modeling of the device to estimate this. You need to assume that something is a qubit, a qubit, a classical system. It can be whatever, but you know, because you see it, that it produces these statistics. So this might seem complicated, but what I'm saying by this is something very simple. I mean, you, for instance, take the simplest case, which is there are two buttons and there are two results. I will use this notation. Okay? What is these probabilities? Well, this is just a vector of numbers. So you have the probability of getting result +1 when I press button 1 and 1, the same probability of getting plus and minus, the same probability of getting minus and plus, and the probability of getting minus and minus. These are all four possible results that you can see between the two boxes. And of course, you have the same four numbers for the other combinations of inputs. Okay, that was when Alice and Bob press button 1, they see these four combination of results with some probabilities. When they press button 1 and 2, they see these four combination of results with some probabilities, and so on. So these are just positive numbers, such that the sum of these four terms is equal to 1, the sum of these four terms is equal to 1, and so on. So this is just a vector of some numbers that satisfy positivity and some normalization condition, standard probabilities. Of course, you have different probabilities that are conditioned on the x and y, and this n depends on how many buttons and lights you had. Okay, so in this case, where you had two buttons and two outputs, this n is equal to 16. I hope this is clear. Okay, I guess this is very simple. Okay, so what's the goal of device independent QKD? The goal is the following. Actually, you can even go beyond device independent QKD, but you can think of device independent quantum information processing. So what you want to do is you want to make protocols that from these numbers do something. So for instance, you can get a key. So if you have a way of proving that from these numbers you can get a secure key, there cannot be any mismatch between what the theory demands and what the implementation does. Okay? Because you go to the implementation and either you see these numbers, you don't see them, but if you see them, you have you can establish a secure key. And if you don't see these numbers, you give the boxes back to these statistics, the one that you need for security, you give the boxes back to the provider, and you don't run the protocol. And this is independent of whether the detector was working in the linear mode or in the single photon mode or whatever, okay? It only depends on whether you see these numbers or not. So this is very good also for certification. So I think this is, well, I think there are some classical cryptographers here, and I think it's very relevant for certification because, I mean, possibly you know better than me, but I think in part of this Snowden affair, there were some documents showing that the NSA was somehow hacking cryptographic solutions from the inside. Okay, so this is, well, in this case, you cannot do this because you have to see these probabilities, and from that you can establish a security. Okay, this sounds like magic, but it's not. And the only reason why it's not, and it's because, of course, the security is proven from these numbers, but you make some assumptions about these numbers. So for instance, you assume that these numbers have been obtained after dealing with quantum devices. You don't know anything about these quantum devices. There might be qubits, qubits living in a hyperspace of infinite dimension. You don't make any assumption about which quantum devices you're dealing with, but you assume that they are quantum. Okay? So this means for those who know about quantum physics, and if not, well, I will tell you anyway. If they are quantum, it means that these numbers that you saw should be written as, I will now explain the notation. So they should be written as measurements, well, measurements for Alice, measurements for Bob. Here there is a tensor product, because there is one box and a second box, and there is a quantum state that is being measured. I'm not saying where these objects live, so this lives in a hyperspace that I don't know. And the same, these operators act on a hyperspace that is completely uncharacterized. But there is a hyperspace, because these are quantum devices. And this is why you can do things. Okay? You can do things because you assume that there is a physical theory behind the functioning of your devices. And now I will tell you a bit more about this. So basically what happens is that when you impose some physical principles, like the devices are quantum, then give some structure to correlations you see among the devices. And by correlations, I will always mean this vector of probabilities. So this is a very mild assumption, especially if you live in quantum physics. If you live in quantum physics, it's not an assumption. It's just telling you how devices behave in nature. But that's enough to prove security of the protocol. Okay, so now I will try to tell you why you can prove security in this regime. And for that, I have to connect with something that is called a Bell inequality. This is a fundamental concept in quantum physics, but of course, I think you may be completely ignorant about what a Bell inequality is, so I will explain you. So what is a Bell inequality? So let me go back to these boxes. As I said, all my talk is going to be about boxes. I like very much boxes. And now I'm going to consider again the same situation as it was the simplest situation. So I have two possibilities here. I have two outputs here. And I want to reproduce these numbers. Okay? So now let's try to think about which numbers I can see here. And now let's try to use common sense. Okay, so let's think for a while and think about what we can see between these two boxes. Okay, so there is a source here that has put some information on these boxes. So if you don't know anything about quantum physics and you think about your common sense, your intuition, you can say, well, in this box, what I did, in the two boxes, I prepared these two boxes together, so they were prepared here. Then Alice got one and Bob got another one. And what I did, I wrote in these boxes the instructions about how they are going to behave. I don't think you can do something different from that, okay? And what are the instructions? So the instructions you're going to write is instructions for box A. You're going to write if x is equal to 1, so you press button 1, A is equal to plus 1. and x is equal to 2, a is equal to minus 1. Okay? And then, second box, you will write if y is equal to 1, say b is equal to plus 1, and if y is equal to 2, say b is equal to plus 1. Okay? I think this is all what you can think of to produce the outputs given the inputs. It's clear. Okay, so another way of writing this is like, I'm going to use this notation now. Here you say that a1 is equal to plus 1, and a2 is equal to equal to minus 1. Okay, I'm just saying the same, but now I will use two variables, a1 and a2, which is output when the input is 1 and output when the input is 2. Okay, and here b1 is equal to plus 1, b2 is equal to plus 1. Okay, so I think this is, in a way, I'm saying a triviality. Okay. So now what you do, you take this combination of measurement, output. Okay? It's just something that exists, that you can measure. So you can press 1, see the result, press 2, see the result, and so on. So it might seem weird, but now you all will understand why I took this combination. Okay, this is something called CHSH value inequality. Well, what you can see, let's compute this quantity for this assignment of outputs given the inputs. Okay, so you see A1 B1 is equal to plus 1, A1 B2 is equal to plus 1, A2 B1 is equal to, okay, I feel somehow ashamed of doing this calculation here for you, but, and A2 minus B2 is equal to minus 1, but there's a minus sign here, so this makes plus 2. Very simple calculation, okay? And now if you repeat this for all possible combination of pluses and minus ones, okay, you can see that this number is always equal to plus and minus 2. Okay. So now you can think of an experiment where it can be that the strategy, I mean, usually what we will do in the quantum regime, I mean, some particles will get some particles for their bounds, okay? So you can think that you change this strategy, you change from time to time. So sometimes, this means basically that sometimes this number will be equal to plus 2 and sometimes it will be equal to minus 2. But of course, if you repeat this, the expectation value of this number will never be larger than 2. Okay, because it's 2 and minus 2, sometimes it's 2, sometimes it's minus 2, so it will be at most 2. Okay. Now, and here, this is, as I said, to me, this is just common sense applied to which correlation you can see between two devices, okay? But if you want a connection with foundations of quantum physics, these are some models that were introduced by Einstein, Podolsky, and Rosen in 1935, just to propose an alternative to quantum physics. So these models were introduced, and then Bell, who was the inventor of Bell inequalities, realized that when you have these models where you assume that the instructions were written in the boxes, you still have to satisfy some conditions. Actually, it's interesting because I've been told that these conditions, like the one here, are in some papers by Boole in the past, like the guy from Boole algebra. Okay, because it makes a lot of sense, and this is just common sense applied to what you can see between two devices. Okay, perhaps the surprise then comes when you can see that these conditions can be validated by quantum mechanics. Okay, so you can now go to the lab, you come here, you prepare quantum particles that go to the parties, you make two measurements, you get two outputs, you estimate this number, S, you repeat the experiment, and you can see that S can go up to 2 square root of 2. Okay, so which is, if you are not surprised, it means that I didn't do a good job here. Okay, because it's surprising. But this is what nature is. Okay, so you can give conditions, quantum mechanics release some conditions where you can get this number, and you go to the lab and you see it. So this means that something was wrong. And then when you come back here, I mean, there is nothing really that can be wrong. Okay, I mean, this was just very simple algebra. So perhaps what was wrong is what our assumption, that the instructions were written in advance, in the boxes. And well, in quantum physics, this is what is happening. So now you connect with Einstein, Podolsky, and Rosen. What Einstein didn't like from quantum physics was the fact that somehow the outputs are not predetermined in advance. There is some component of intrinsic randomness. And this is why he didn't like quantum physics, and he wanted to have other models with no randomness. But what you can see is that if the results are written in advance, like what I said here and here, then you satisfy some conditions, but these conditions are violated. So it cannot be that they are written in advance. And I was told that Renato was explaining the Ecker protocol, and some of this is the intuition behind Ecker protocol, because in Ecker protocol, you construct the Bell inequality from a violation of a Bell inequality, the protocol from a violation of a Bell inequality, and you know that the eavesdropper cannot have a perfect knowledge about the output of your measurement, because if this was the case, the eavesdropper would have something like this. Okay, if he had a perfect knowledge of what the measurement is going to do, what the measurement result is going to be on Alice and Bob, the eavesdropper would have a list of these numbers, but then the numbers would be satisfying this inequality. And since you see a violation of a given inequality, no one, not even the eavesdropper, can have a list of these numbers. And these numbers are random to him, or to her, sorry. Okay. So this is somehow the idea, okay, of devices as an QKD. So what you have to do then, you have to go to the provider, you ask these two boxes, you check them, you construct these, and from these you can compute what is a Bell inequality. And from that you may hope to get a secure key. Okay. And now, okay, this is now the intuition why it works. Okay, now I will give you a sort of proof about it. It's not a proof, but I will tell you an argument that it works for the ideal case. So that was a Bell inequality where I wrote these weird parameters A1, B1, and so on, that was bounded by 2. And I was telling you that in quantum physics, you can get up to 2 square root of 2. Okay? So now you go to the provider, okay, this is an ideal situation. This is the maximum you can get within quantum physics. This is what you get, you have in a noise-free situation and everything works perfectly, which is never going to be the case, but let's assume that we are, I mean, for the time being, let's be pure theories, and let's see what happens if you are in this at this point. So when you do then, you go to the provider and you ask two boxes, one for Alice, one for Bob. The two boxes have two buttons, they produce an output that you call plus and minus 1. You check them, and from this you can compute this number. I mean, you have to repeat, sometimes measure 1, sometimes measure 2, sometimes getting plus 1, sometimes getting minus 1. You do this many times, you can estimate the value of this quantity. And imagine that you get 2 square root of 2. And now the assumption is that the devices are quantum. Well, there is a known result that was obtained in the 80s by a mathematician called Sidelson. And he proved that the only way, I mean, if you think about a quantum state and measurements that give you this number, there is only one way of doing this. Among all possible Hilbert space you can think of, all possible measurements acting on this Hilbert space, all possible states living in this Hilbert space, there is only one way, which is you are measuring what is the maximum entangled state of 2 qubits. And you are making measurements on the blocks here that are, say, let's be consistent with what I wrote. Zx, this is for Alice. So this is the observable that defines A1, A2, and this is B1 and B2. So what Sidelson proved was that if you take this state, the maximum time state of 2 qubits, you give one particle to Alice and another particle to Bob, and Alice applies these two measurements on the z and x direction, and Bob applies this measurement, which is z plus x divided by square root of 2, and it is minus z plus x divided by square root of 2. Okay, these are some operators acting on inverse of dimension 2. You apply these measurements, you can see that these measurements acting on this state gives you this amount of Bell equality violation. But these are the only states and measurements that give you this amount of Bell equality violation. Okay, so this was an idea introduced by Myers and Yao. It's self-testing, which is very powerful. So it just means that if you get two completely uncharacterized boxes, where you can implement this, you have these two buttons and two lights, and you can see this number, just this number is telling you all the information you wanted to know about these boxes. So these boxes have this quantum state, and they are implementing these two measurements. Of course, I mean, you have some freedom, which is, okay, maybe, sorry, here there is this. Okay, maybe here you have another system, and these measurements are not acting on this system. And maybe here, what you have are not these measurements, but a local unitary acting on these measurements. And the same unitary is acting on this state. There is a trivial freedom, let's say trivial, okay, which is irrelevant for you. I mean, whether it's zeta x or another local unitary rotation acting on this, you don't really care about it, okay? Or whether inside the box there is another quantum system, but actually you aren't measuring this quantum system, for you it's also irrelevant. Okay, for you what matters is that to get this statistic that gives this, you are acting on this state and you are acting with these measurements. So what happens when you apply these measurements on this quantum state? So again, you go to the provider, Alice and Bob, they ask these two boxes, they get the two boxes, they measure, and they see this magic number 2 square root of 2. So what I know immediately is that they have this state and these measurements. So since they have this state, they know that the state is pure. Well, here I will tell you something that I'm not sure if everyone will follow, because this is a result of quantum physics, but in quantum physics, if you have a state which is pure, okay, it's a vector, then this state cannot be correlated with anyone else, including Eve. So by looking at this 2 square root of 2, you know that the state that you are measuring is not correlated to anyone else. So whatever this person outside does with a possible quantum particle, this quantum particle cannot be correlated with these two particles. Because if it was the case, the state wouldn't be pure, and in particular wouldn't be equal to this state, and it wouldn't give this violation of the Bell equality. So you certify that the state is the one you want, and moreover it's pure, so Eve cannot have any information. On top of that, this state when you look at what Alice has, the reduced state, I mean here I'm using some quantum stuff for that. When you trace out Bob's particle, this is the quantum state, and you apply any projective measurement on this state, you have this probability, the probability of getting +1 is equal to 1/2, and the probability of getting -1 is equal to 1/2. Okay? So when you make projective measurements on this state, you know for sure that you're getting something that is completely random and cannot be predicted at all by an eavesdropper. Okay? And by repeating this process, what you manage to get then is a secret key. Okay, so this is basically the idea. Okay, so you go, you buy these two boxes, you see a violation of a Bell inequality, and I took the ideal situation, which is you get the maximum value you can get, 2 square root of 2, and then you know that Alice and Bob, by running this protocol, they will get a secret key. Okay, because, okay, what I said is not, let me just say something. So remember, these were the bases used by Alice and Bob that were certified by the Bell violation. That was the state. Let me be precise. So if you want to establish a secret key, Bob has to add one more basis. correlated to one of the two, because then these bases and these bases are used to construct the secret key. Because these are the bases you measure 0. If the bases are identical, when you measure 0, you get 0, and when you get 1, Bob gets 1. Okay? I hope it's more or less clear. What I mean is that now these were the two bases used by Alice and Bob to certify the state, but to construct the key, Bob adds a third basis that just gives the perfect correlations between the results. And this doesn't do anything bad to your protocol, okay? Because the certification comes from these bases that are used to make to estimate the violation of the Bell inequality. Okay, so this is the idea. Now, of course, what happens is that when you go to practice, you will never see this number, because this is what you need. For you to get this number, you need ideal states and ideal measurements, and this is never going to be the case. So the idea of device-dependent QKD is then, okay, if you have a Bell inequality violation which is larger than the classical case, but it's, okay, let me see. But it's perhaps not the ideal one that you want, but still. Then you should prove whether this Bell inequality violation is still good enough for you to prove security. And then there are security proofs about that. There are not many, I must say. So I think the best results are given by Miller and Shi. And the proof security, okay, I must say I was trying to decipher the number in their paper, I was not able to find it. I think they give a security proof that works for a small deviation from the ideal case, but I cannot tell you the exact value. Okay. So we have some, in my group we got some results under some conditions, so it's not a fully general proof, and then the epsilon can be made larger. But in the general proof, I think we still live with a small epsilon, which is a problem for the implementation. Okay, so again, this is the idea of device-dependent QKD, which is nice because in particular, the attack that I was telling you with the detector, so now you can say, okay, let's go to the lab. Again, what I need to that, I don't have to make any assumptions, so there is no mismatch between theory and implementation, so this protocol is secure. So if you think, for instance, the attack that I was telling you about before, this Makarov attack that plays with the detectors and forces the detector to give a given click depending on the condition, well, this attack does not hold, okay? Because if someone from outside can force the detector to give a click, this is the same as specifying from the output, from the outside, the output of the detector. But this is not possible, okay? So if you see a Bell inequality violation, these sort of attacks are not possible. And this is certified by the Bell inequality violation that you see. Okay, so this is a very nice idea, so let me just finish why this is not happening. Okay, that's very nice. Well, the problem is that to see a Bell inequality violation, okay, I was telling you that we have seen Bell inequality violations, which is true, but to see a proper Bell inequality violation is a difficult experimental problem. Okay, this is because what you're going to do then, you have to see a Bell inequality violation between these two devices. Okay, remember X, Y. No, I'll change the color here. I don't know why I had. Okay. So X, Y, A, B. So this is the level of the user. He wants to get this box, or the user, they want to get these boxes. Now I'm the provider, so I have to make sure that I can prepare these boxes. So I have to prepare some boxes that produce a Bell inequality violation. So what I will do, I have to prepare some quantum particles here, or send some quantum particles, and I know that Alice and Bob are going to implement some measurements on these quantum particles. But Alice and Bob are distant, so there is a, here, say, a reasonable distance between the two. So I have to send quantum information between these two parts, between these two distant locations. So the best method we know to send quantum information is with photons. So the provider sends photons here, and they travel through a fiber optic. But perhaps you remember what I said, every channel is lossy. So most of the time, and the photon is very tiny, very tiny intensity, okay? So what happens is that most of the times the photons don't reach the devices. So then this means that instead of having plus minus 1, you have a third result, which is no click. So the photon didn't make it to the device and you didn't see any click. Okay, sorry, I was using plus and minus. And this means that instead of getting this correlation that give you 2 square root of 2, or whatever, you get some different correlations that are not even defined in the same alphabet, because now instead of having 2 outputs, you have 3 outputs. And what happens, I don't have time to tell you, is that if the losses are moderate, I mean you don't need a big number, then P, A, B, X, Y don't violate any Bell inequality. And if, okay. And if the statistics you see don't violate any Bell inequality, okay, then you cannot certify security in this device net regime. Okay, so this is a problem. And now just for me, okay, and this is a problem because losses that are small, as soon as you put some kilometers, so for instance, if you take the CHSH, the amount of losses you can tolerate are equal to 2/3. And if you think about a channel, the losses go exponential with distance. Usually they are written like this. So I think this amount of losses you immediately get after, I don't know, 5 kilometers or whatever, okay, or maybe 10 kilometers. I don't know, well, this I don't remember, but it's just a small number, okay? So it's a protocol that is insecure after this. So what you have to do then, and this will conclude my talk, so this is difficult, okay? So there have been Bell tests, but usually the Bell tests that people have, the demonstrations, actually this was, 2015 was a good year for Bell test demonstrations because they were very good experiments, but of course they were experiments made in some very ideal conditions. Many of them were on an optical table, okay, where there is one setup here, one box here, and another box here. And of course, this is not useful for cryptography. You want cryptography, I have a box, and my friend has another box in a distant location. So the way you have to solve this is the following. So the particles are prepared. This is the way we know. You have to do 2 boxes. And now the photons are prepared, they are sent, and this box is something called non-demolition measurement. So the box sees whether the photon has arrived or not. So suppose this box says, hey, photon, my friend, are you there? And then you get yes or no. Okay? So if the photon is there, the box says yes, and the photon is not there, the box says no. Okay, so this is a quantum non-demolition measurement. So if the 2 boxes say yes, then you run the Bell test. And if one of the boxes says no, you throw away the data. Okay, this is inefficient, but in such a way, you do it in such a way that the Bell test is implemented only when you are certain that you are going to get a result. And this is not a problem. Okay, this is a theoretical solution for the implementation problem, but of course doing this non-demolition measurement where you see whether a photon is there without destroying this photon is very complicated. But okay, in principle, it is possible. Okay, and the last thing I want to tell you is that this is also general, and also it can be applied to another problem that is also of cryptographic interest, which is the problem of randomness generation. Okay, so I always use the same example to motivate this random generation, which is, imagine you want to have a random number generation and you go to a provider, and okay, now we'll do it in a very extreme situation where the provider is against you. So you have a virtual casino and you want to have a random number generator to run your virtual casino. So you go to the provider and you say, and the provider knows that you have the virtual casino. So you say, okay, I want a random number generator. And then the provider has very good technology. He has a quantum random number generator, or a very good random number generator. So what he does before you come, so for instance, he knows that you're going to run some statistical test, but he knows the size of the change you're going to use for the sequences you're going to use for the statistical test. So before you come, the provider generates random numbers. He copies these random numbers into a memory. He puts this memory into a box. He paints the box with fancy colors. He writes a quantum random number generator. He charges you twice the price, and he gives you this box. Okay, so you go to your, again, you say, is this a random number generator? And the provider tells you, yes. And you say, but it's quantum, the provider tells you, yes. Then you go with your box to your lab, and you want to make sure that it's random. So you start generating numbers. And of course, these numbers were generated with a very good random number generator, so they pass any statistical test. So you think, oh, the provider was a good guy. So you start using these numbers. But of course, I mean, okay, they are random to you, but they are not random to the provider. So the provider can wait until you use them in the virtual casino and gets all your money. And again, this is a problem of certification. Okay, how can you certify that something is random? And I think this is a problem, especially for quantum solutions, because you go to the provider and you say, but is this quantum? And the provider will tell you, yes. But then you certify with statistical tests that are passed by also classical random number generators. So how can you even certify that something is quantum? There is a quantum origin for your data. And the solution is again the same as I was telling you before. So you go to the provider and you ask two boxes with two buttons and two lights. And now you run the test and you look whether the statistics you see violates a Bell inequality. If it does, you keep them and you run your virtual casino with some of the outputs. If not, you give them back. Now, well, first of all, you can see that this is a certification of quantum origin because classical correlations don't violate any Bell inequality. So if you see a Bell inequality, you know for sure that the provider had to use a quantum effect for declaration. So it's an intrinsically quantum solution. Because using classical information theory, as I proved to you, you can never violate a Bell inequality. And on top of that, you know that these instructions were not written in the boxes in this classical memory because you saw a Bell inequality violation. And for instance, something that you can do, we get some techniques, was you may want to see, remember this could be plus and minus 1. There are techniques that tell you what's the amount of predictability that an eavesdropper that might share correlated information with the devices has on the output as a function of the Bell inequality violation. And the typical curve you get is something like this. So you have here, say, the CHSH, remember? That was the classical value, that was the maximum quantum value. And you estimate the predictability here. What's the probability that I can make a guess that if I make the guess that this plus 1 is correct? And you can see that it starts at 1 at the classical regime, but then it goes down up to 1/2. So here you have a perfect random gate. Remember that I proved by showing that at this point Alice knows that the state in the two boxes is equal to this. Okay? But you can get a curve here that tells you how some of the randomness in the device is connected to the Bell inequality violation. And all this region here is simply impossible with quantum physics. So if you had a point here, quantum physics would be wrong. Since we believe that quantum physics is correct, you have this amount of randomness that is certified by the measure Bell inequality violation. Okay, I've had some other things to say, but I think that was basically the main motivation for me in devising an QKD, so I think it makes sense to stop here. Thank you very much.
We have time for one or two short questions. Yes.
Can you comment a little bit how is it possible to extract randomness if you don't violate the Bell inequalities in the maximal way? So you mentioned this paper by Miller and Shi. Can you comment a little bit on that?
Yeah, okay. Okay, so it's a good question because it made me think that I forgot to mention some things, okay? Of course, in these boxes, there are some conditions you have to meet for this to be a proper bell test. Okay, so one of the conditions is maybe I start a new. Here. Yes. So what is a proper bell test? A proper bell test is what I wrote. Okay, this is a proper bell test. Okay, it might seem something very simple, but okay. What I mean by this is that you need to make sure that you are dealing with two boxes. Okay, because if you're not dealing with two boxes, that test doesn't make sense. Again, how can you certify that you're dealing with two boxes? So, well, you have to make sure that there was no communication between these two boxes. Okay. So if you are in a completely parallel scenario, well, there are several ways. I think you can somehow have some information shielding of your boxes, but in a completely parallel scenario, you can arrange the events here, the measurements, so that they define space-like separated events. So there is no time, not even for light to travel from one location to the other. And then, since the devices don't communicate, you can assume that you are dealing with two boxes. So this justifies that I'm dealing with two boxes. And the second thing you need here an input. Okay? So this means there is something that it was not known at the moment of the preparation. If you want, it was random at the moment of preparation. Okay? So it means that these numbers here that you use as an input could not be predicted in advance. Because if they were predicted in advance, you could have produced them inside the box and you wouldn't need this input. Okay? So this is also a second assumption. Okay? So, for instance, a way of justifying this, you may think that what I'm going to use for the input is going to be the first letter of the newspaper that they are going to use. Okay? And I assume that the provider didn't have this information when he prepared the boxes. Again, this is an assumption, but for me it's a safe assumption, but okay, it's an assumption. So you need these two assumptions. Okay? Let's assume you are happy with these assumptions, you see a bell test. So if you come back here, so you see a bell negative evaluation, which is not the ideal one, but it's somewhere here. Okay? So this means, okay, I'm going to give you some sort of intuitive explanation. Okay? So you see this bell negative evaluation, so you have these curves that tell you that you have this lack of predictability. So you can predict the output, but not fully, okay? Because if it was fully, your predictability would be equal to 1. So you have this lack of predictability. So the eavesdropper has this lack of predictability. So this lack of predictability, basically what it tells you is that by repeating the process, you generate bits with a given entropy. Because they are entropic, because they cannot be fully predicted, although they are not fully entropic because you are not in this quantum maximum evaluation. Then what you have to do, basically you can certify that by running the process n times, you have a sequence of bits. So n bits, you run it a given amount of times, and using the bell negative evaluation, you can certify that the entropy, the mean entropy of this bit is larger than a given value k. Okay? And now, for that, you would need to use what is called a randomness extractor, for which you read a random seed. Okay, so rather than randomness generation, if you want is randomness expansion. So now you take a seed. Well, these probably people in the audience know much more than me. Okay, so you take a random seed, and in randomness extraction, you have a sequence of bits of a given length, and you have a promise on the amount of entropy. You can take these two and distill a sequence of k bits. Sorry. With the same entropy as before. And k bits with entropy equal to k are k random bits. But for that you need this seed, but this seed I think can be of logarithmic length. Okay? So the process is, you run the devices, you see a direct evaluation. You use some theoretical machinery that tells you that the amount of entropy in your outputs is bounded by a given quantity, which is this is a function of the direct evaluation. And then, once you have this, you run an extraction process, and you get the final list of random bits.
Okay, so let's thank the speaker again.